Welcome back to lesson 3. This one's on power functions, and I'll be honest, this is going to be a fairly short one because these are straightforward. This is going to lead us into our next lesson on polynomial functions. So again, we haven't really talked about polynomial functions as a whole yet, but you have seen linear and quadratic functions so far. Linear functions tend to be in the form of y equals mx plus b. Let me just actually write that down over here. So y equals mx plus b. And quadratics tend to look like ax squared plus bx plus c. And despite the fact that the coefficient variables m and b are a little bit different than the a, b, c at the bottom, they're basically in the same form of something x plus something, something x squared plus something x plus something. And then I think you can imagine that as we continue, it'll be something x cubed plus something x squared, etc. And we'll just keep that pattern going. A power function is actually a simplified version of these, which is just in the form of f at x equals ax to the exponent b. So basically, we have some number x to some exponent. Quadratics, if the only thing we had was ax squared, that would be a power function. As soon as we add in the bx and the c, it's no longer a power function. Same thing, linear, we have mx, that would fall into this form. As soon as we add that b value, it's no longer there. So here we've got that, and I want to point out that it's important to note that a is the element of real, which is basically a fancy way of saying that a is any real number. It could be 7, it could be 23.8, it could be negative 1/3. So it can be anything. B, on the other hand, is the element. And for those of you who haven't seen this notation before, we'll be using it in just a moment anyway. Element just means it belongs to the set of, or it is one of these kinds of numbers. It's actually going to be a whole number. And I know I drew the R and the W there a little bit weird for real and whole. That's just a mathematician notation. It's more of a font thing than it is an actual like different symbol thing. We tend to write number sets with kind of a double bar at the beginning. If you don't do that, that's absolutely fine. Obviously, when you're typing stuff in, finding that symbol is going to be difficult. Just type in an R or a W. No issues there whatsoever. Okay, so if we start off with some of the basic ones, f at x equals a. A is just a number. There is no variable in it whatsoever. We call that a degree 1 function. Sorry, we call that, I'm jumping ahead of myself. We call that a degree 0 function. And that's just called a constant function. So for instance, you might get f at x equals 5. Well, it doesn't matter what the input is. The output's always going to be 5 because there is no input taken into consideration. The next one is degree 1. The exponent on the x is the 1, and it is a linear function. And likewise, ax squared is degree 2, and it is a missing letters here, quadratic function. And then if you're not familiar with the next two, you may not have heard them yet, but they're going to be degree 3 and 4, and they are cubic functions, kind of like x squared. Well, x to the exponent 2 we call x squared, x to the exponent 3 we call x cubed. So that's why it's called cubic. And then this one would be quartic functions. And there's names for ax to the 5th and ax to the 6th and ax to the 7th as well, but we're not going to worry about calling them by specific names. We'll just say they're degree 5, 6, 7 functions, whatever they happen to be. We don't need to memorize special names for them. Now, before I get into this next part on end behavior, actually, you know what? I'll just kind of jump in real quick. End behavior basically says, what does this graph look like if you look at the extreme left and extreme right-hand sides of the graph? So for us, we're going to look over here and over here. And for this one here, it's actually really easy to describe right now. We're going to simply say that it starts low down here in the bottom left. So we'll say it starts low And up here at the top, it ends high. That's the easy way of explaining it. Starts low in the bottom left, ends high in the top right. This may not seem important, but it actually tells us a lot about what the graph is. Okay, we're going to be more specific as well, and I'm going to show you this notation now. You can use it if you'd like, but you're welcome to use starts low, ends high, or starts low, ends low, starts high, ends low, whatever it is. But this other notation will be needed a little bit more in a future unit, so we will come back to it. But another way to describe this would be to say that as x goes to negative, I drew infinity like an 8. As x goes to negative infinity, so basically it's saying as x goes this way, what happens to y, and y also goes to negative infinity. And as x goes to positive infinity, y goes to positive infinity. So we basically just look at what happens to x as it goes to negative infinity or positive infinity, which is really a fancy way of saying what happens as it goes to the left and what happens as it goes to the right. In this case, as it goes to the left, we go down, so x goes to, or y goes to negative infinity. And as we go to the right, it goes up, so y goes to positive infinity. I'll let you fill in this table on your own after, but I'm going to actually just jump over to Desmos for a second, and we're going to kind of see what happens over there. So in Desmos, I'm going to punch in a generic power function. I'll just leave the a as 1 right now. The coefficient really, actually, you know what? Oh, let me just try this. Ax to the exponent b. There's our general form, and you'll notice that it asks me, do I want to add these sliders? And I will say, sure I do. So by default, it gives me a equals 1 and b equals 1. So I could go down to b equals 0, and you'll see there's my constant. And you know what? I'm going to do this. I'm going to go b equals 0 up to 10. And we can step by different amounts. And then we see what happens as b increases. 3, 4, 5, 6, 7, 8, 9, 10. Okay, that happened really fast. Can I slow this down? Oh, I'm going to slow this down a little bit. I'm going to slow it down to 1/3 time roughly. Okay, so what's going to happen is I want you to take a look at the picture and what it looks like as b goes up in value, and I will not get it to repeat. Just watch what happens to the shape of the graph. So exponent on x is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And I think what you can see is that in all situations, if it's an odd numbered one, like let's say 3, we start off in the bottom left corner and end up in the top right. And if it's even, we start high and end high. Odd, start low, end high. Even, start high, end high. So they all end high, all of these. The only difference is we start at different highs and lows depending on whether the exponent is even or odd. A good way to remember it is if you remember that a linear function default looks like this, starts low, ends high. That's the exact same for all other functions that have an odd exponent. And likewise, parabolas start high and end high, or start low, start high and end high. I'll get this straight. Start high and end high, and so do all even functions. 4, 6, 8, and 10. The only difference is they get a little bit steeper quicker. They start off more more flat at the bottom, but they go up then very quickly. And that's the only difference between the different evens. But the good news is if we look at these and we say, oh, it starts high and ends high, we know that the exponent's even. And if we see that it starts low, ends high, we know that it's odd. Now there is one exception to that, and that is that if I change the coefficient to a negative, so I'll change it to -1, then it does the exact opposite. We start off with a negative slope, which means that we start high and low, and then it's going through these all. You'll notice these all end low, but the starting one flips. And again, it basically does the opposite of what happened when A was positive. Now, does A have any other effect on the graph? The answer is probably. So what I'll do here is I'll just go through, let's say -10. Oh, sorry. I'll go -10 to 10, +10. And if I go through this, got to make sure my animation settings are correct here. There we go. You'll see that this is what the A value does. When it goes from negative to positive, it flips the graph top and bottom. But as far as the actual rest of the values go, once it's positive, the end behavior is the exact same. It starts high, ends high, starts high, ends high, starts high, ends high. So the A has no bearing on the starting and ending positions except for the flip up and down. But once the actual value itself is meaningless, whether it's odd, even, a decimal number, does not matter. All right, so going back over to our paper here, we noticed that when A is positive, which is basically all the stuff on the left, we always ended high. Always. Always, always, always ended high. And when we started off with an odd exponent, 1, we started low. And when we had x squared, we started high, like a parabola. And then low, high, low, high. So we just alternate back and forth. And if the coefficients are negative, we always end low. And we started off high and ended low, high, low, high, low. Forgive my abbreviations. I'm really lazy and hate writing more than I have to. Okay, so what that means is that if we look at something like this weird function down here, y equals -28.6 x to the exponent 163. If I asked most people what that looked like, they'd have no idea. It would be crazy looking. But all we need to know is what its end behavior looks like. So the fact that it's an odd number, actually, you know what? Let's start first. The fact that it's an even coefficient. I said both those wrong. The coefficient is negative. The coefficient is negative, which tells us we're going to end low, because we always end low when the coefficient is negative. And the fact that it's odd tells us that we start high. So start high and low. And it's going to look basically not that much different than a negative cubic function, but it's going to be a lot flatter at the middle part and a lot steeper after that. So if I flip back over, switch to here, we'll punch in, let's get rid of those. Negative, actually I'm just going to leave that as negative. That's what negative x cubed looks like. So that's basically the same idea. It's a negative odd exponent power function. And if we change this to -200 and, sorry, what was the number that we were using? -28.6. 28.6. It still has the same quality of start high and low. And then if we change this exponent to 163, okay, it looks super abrupt there. Now, again, I think I mentioned this before about smoothness, and that's that all polynomial functions and power functions are polynomial, are going to be smooth, and some people are going to look at this and say, no, 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 it's sharp there. I'm going to just zoom in for a second, and when you zoom in far enough, you'll see that there's never any sharpness. It's always smooth. It's just, if it's smooth on such a small abrupt scale, it looks sharp. But always, if you zoom in enough, it will be smooth. Okay, let's jump back here. So that's what that function would look like, and we can predict what it looks like just based on the fact that the coefficient is negative and the exponent is odd. All right. So that's pretty much it for power functions, is recognizing the high, low, and how the effects of the A and the B change the way that the graph looks. I'm going to start talking about domain and range with this lesson just because it was such a short lesson otherwise, and we're going to be using domain and range as we go forward in all function types. So you'll note that the examples I'm doing here are not actually power functions. They're just general looking functions. Some of them we won't even get into in this course, but the ideas of domain and range kind of go beyond any of the stuff that we have to worry about as far as what kind of function it is. So domain and range of a function, domain in general, is just a fancy way of saying what are all possible inputs. So what are the inputs that I can put into a function? And not all functions can have any input put into them. For instance, if we have the square root of x, I realize this is not one of the functions we're doing, but I can put in 5, I can put in 23, I can put in 100, but I can't put in negative something. I could put in 0, but I can't put a negative number in there. It breaks the function. So negative numbers are not part of the possible inputs. They're not part of the domain. Likewise, range is all possible outputs. It's just saying what are the possible things to get out of this. Now, if I take a look at that first graph that we're looking at there, it's just a parabola. It's just a quadratic function. And we know that for a parabola, something in the form of y equals ax squared plus bx plus c, I can plug in any x value I want. I'll never break it. But in this case, the outputs only go up to a maximum of 3. There are no outputs above 3. I can't find out where the graph is at when y is 4. So our domain, we can express domain and range basically in the same way as each other, except one's in x and one's in y. But we can express it in two different ways. Depending on the situation, sometimes one's nicer than the other. So what we can say is for the possible inputs here, x is the element of real. And I'm sorry, I should redraw that abomination. These should be the nice squiggle brackets that look like that. That's the notation for inequalities. And the set notation, when we want to say it can be any possible x value, it looks like this: negative infinity, comma, positive infinity. So it basically says what's our lowest possible value, what's our highest possible value. So the first one is just saying x is any real number, and the second version is just saying it's anywhere from negative infinity to positive infinity, which is pretty much the same thing. Now, some people might ask why the first one's called inequality when there's no inequality there. When we get to the range, we have a little bit of an issue. So we'll start off with the same squiggle bracket. I'm going to go over to the left a little bit more here because this one's going to be a little longer to write. And I'm going to say y can be any real number such that. So a big vertical line that just basically says there are some restrictions here. I'm going to list them. And the list is my y value can be 3 or lower. So it can be 3 or lower. So I say y is less than or equal to 3. And then I close the brackets. In the first one, there were no restrictions, so we didn't put them. For the domain, in the range, there is a restriction. Y has to be less than or equal to 3. So we just state y is any real number such that y is less than or equal to 3. Now, similarly, here I'm going to put a bracket that says I can go down as low as negative infinity, but my maximum value is 3. And it's going to get a square bracket this time. Now, the difference between the round brackets and square brackets in set notation is that a square bracket tells you that the number is included. 3 is included. If I want it to be strictly less than 3, then I would say a round bracket there. But if I want to include the 3, square bracket. Infinities always get round brackets, and the reason for that is infinities are concepts, not actual numerical values. I can't do mathematical like operations on infinity. There's no such thing, because some people would say, well, half of infinity is smaller than infinity. But that's not true. They're both infinite. They're both forever. They're both never ending. So we always use round brackets for infinities, and we use round brackets for almost but not including endpoints, and square brackets for including endpoints. But let's see this with more examples. Okay, here we have another parabola. So it's going to basically be pretty similar. Domain X is the element of real. And my squiggly brackets will continue to just deteriorate as time goes on. That's just part of my handwriting. Set notation, we can go everywhere from negative infinity to positive infinity. Range, in this case, we have a minimum amount on our parabola, and that's -2. So we say y is a real number such that y is greater than or equal to 2. And here our low value, I'm jumping ahead of myself. Our low value is -2, but it can be -2, so it's square. And our high value is infinity, which is always a circle bracket. This next one is actually a root function, a square root. We don't need to know that. We don't need to know its formula. We just need to look at the picture. And this time there is some restrictions on the inputs. The input has to be -3 or larger. So we say x is the element of real such that x is greater than or equal to -3. And likewise here we have a minimum value of -3, but -3 is included, and a maximum value of infinity, round bracket. Range, we have a -4 there, so it's got to be higher than -4. So y is the element of real such that y is greater than or equal to -4. And -4 is our minimum, infinity is our maximum. And finally, we have a weird one. This is another type of function that we will not be covering. By the way, anyone who's taking this course as a bridge to get to the advanced functions, you'll cover these types, these couple extra types, but all the other terminology and rules are basically the same. It's just you'll be applying all the things to new versions or new types of formulas. So in this one, this is actually a reciprocal function, which basically means 1 over x or 1 over some sort of linear relationship. So it can be anything. It looks like the x can't be 2. Looks like it could be anything other than 2. There's an asymptote there. We'll talk about that later at some point, but x can be anything less than that or bigger than that, but it can't be exactly 2. So here I'm just going to say x is the element of real such that x is not equal to 2. And I'm going to leave the set notation for just a second because it's a little bit weird on this one. The range can be anything except 1. I can never get an output of 1, but I can get less than 1 or more than 1. So y is the element of real such that y is not 1. For our set notation, before we said what the minimum and maximum were, here we kind of have two pieces. We have like the low half and the high half. So what I'm going to say is we have negative infinity up to 2. Now this time 2 is not included in the x's. 2 is not allowed, so that means we get a round bracket. And then I'm going to use this symbol u to represent union, which basically means we're going to do that and include this part here, which means we continue at 2 or just above 2 and go to infinity. So this says everything from negative infinity up to 2, but not including 2, and anything above 2, but not including 2, up to infinity. And then similarly for this one, we can go negative infinity up to 1, but not including 1. And we can go from 1, but not including 1, to infinity. So we can't do them as singular. So I know that for many students like set notation for most things better because it's a little bit shorter to write. For special ones, certain situations, I actually like the inequality one better. The set notation with the unions of multiple sets is kind of weird. Either way, that's pretty much all there is to domain and range. Domain, all possible inputs. Range, all possible outputs. And here's some problems that will just kind of check your understanding of power functions and domains and ranges and all that stuff. Give them a shot. Check the answers at the bottom. If you're getting them right, fantastic. And if you're not, make sure you let me know and I can help you out. All right, we'll see you in the next lesson.